So I will start out with a small disclaimer. My voice might disappear, so, but Carlo Evers will have to jump in that case. But so it's very much an honor for me as the Scientific Managing Director of GSI and FAIR to welcome you all to this very special colloquium in memory of Hans Joachim Specht. And as you know, Hans was, among many other things, my predecessor here as Director of GSI. But first and foremost, a distinguished scientist and an outstanding personality in our field of research. And I will just now introduce today's host, Volker Metag, who will be hosting this event and presenting the invited speakers. And a few words on Professor Metag to start with. He studied physics at the Technical University of Berlin and the University of Heidelberg, where he received his PhD in 1970, and then held postdocs division at the Max Planck Institute for Nuclear Physics in Heidelberg, the Niels Bohr Institute in Copenhagen, that left some traces of Danish, I just realized, and the University of Washington in Seattle. And he received, together then with Dieter Habs, the prize of the German Physical Society in 1978 for the spectroscopy of fission isomers. And then from 1982 until 2012, his retirement, he was a professor of experimental physics at the University of Gießen. Pursuing research in hadron and nuclear physics, and also being a member of several international research collaborations, and served on numerous scientific advisory boards and co-editor of Physics Letters B. And also, very important to us here, from 1993 to 1998, he was the research director of GSI here in Darmstadt, and as such, very much involved in shaping the early stages of our bright future at FAIR. So please, Professor Metag.
Well, thank you very much for the introduction. Liebe Frau Specht, liebe Familie Specht, dear colleagues, also from my side, welcome to this special colloquium in memoriam of Hans Joachim Specht, who was really an exceptional and brilliant scientist, and many of us owe a lot to him. But he was not only a scientist, he was also a pianist. And so in order to get you into the right mode of this colloquium, let's start with some music. And we are very glad to have Utku Hasan here. Utku Hasan, sorry. And he will play, let's see what he will play. This. Nocturne number 20, sharp minor opus posthume. Just a few words to Utku Hasan. He is a graduate from the Musikschule and Hochschule für Musik und Darstellende Kunst in Frankfurt. So that's, and he's a graduate from that, but he is already well known. He has successfully participated in several international piano competitions. And I looked up his calendar. He will give a few concerts here in the Frankfurt area in the next couple of days. And we are very glad for having him here. And he will now play Chopin Nocturne number 20. Okay, go ahead. Thank you very much, and I promise you we will hear him again at the end. Yeah, Heinz Specht was a scientist who had various interests in different fields. And just to show you, this is a figure that displays everything. Namely, he was interested in atomic physics, he was interested in nuclear physics, in fission. He studied heavy ion reactions at CERN energies, looking for the quark-gluon plasma. He made cancer therapy a reality. And he also, as I said, he was interested in music. He loved music. And as a scientist, he also analyzed music. And there are very interesting articles in neuroscience about this musical perception. Now, as I said, he has a broad range of interests, so we need at least 3 talks to cover something of that. Namely, Axel Drees will talk about the thermal fingerprint of the quark-gluon plasma, Jürgen Debus on ion beam therapy, and Dietrich von Haar will then give some personal remarks on his experience with Heinz Specht. And my task is to guide you through this program today and also to cover those research areas which will not be covered in this experiment, in these talks. Well, in all these fields, Heinz Specht followed the guideline that was given to him by his PhD advisor, and this is do something new to see something new, Heinz Meyer-Leibniz. And that is really what he followed. He really pushed all the fields to the limits. And I can tell you, working with him was quite a challenge. Well, if you want to hear more or learn more than you will hear today, I recommend to you to have a look at this book. It is in this book, with the foreword of Carlo Rubbia, Heinz Specht describes his own scientific career in his own words, and we have then combined that with contributions from various collaborators and friends and colleagues working with him. So let's briefly discuss his curriculum vitae. He was born in 1936 in Unna, in Westphalia. He attended school at Gymnasium in Kamen. He studied physics at the LMU in Munich, at the ETH Zurich and TU Munich. He did his PhD in atomic physics at the Forschungsreaktor Munich, FRM, with the advisor, as I already mentioned, Meyer Leibniz. He was then postdoc for 3 years at Chalk River Nuclear Laboratories in Canada. He returned to Munich, did his habilitation there in 1970 and became associate professor in 1971. And in this period, 1971 to 93, he did his famous fission isomer experiment that I will explain in a moment. And that made him really known worldwide in the physics community. And it was clear as a consequence, he got a lot of offers for full professorships, and he accepted the one from Heidelberg. And there he stayed until his retirement, official retirement. He did never retire, but his official retirement in 2004. Now, in very important, 1992 to 1999, as already mentioned, he was scientific managing director of GSI, and you will also hear about this period. And in 2000, he became member of the Heidelberg Academy of Sciences. And as already mentioned, he had a broad field of research interests: atomic physics, nuclear fission, ultra-relativistic heavy ion collisions, and neuroscience, musical perception. He was member, founder, and chairman of various collaborations at CERN. And he did a lot of service to the community by being member or chairman of numerous national and international advisory committees. Now, let's begin with his start in the scientific career, and that is the work done at the Forschungsreaktor Munich. He proudly reports in his biography that he was among the first who did experiments with a heavy ion beam, namely with mass-separated fission fragments emerging from this reactor here, and with intensities of 300 ions per second, 300 ions per second. Well, that was good enough for doing some studies in atomic physics. What he actually did was he measured the, I forgot, may be important. You see, Meyer Leibniz was the official advisor in his PhD, but the real one was Peter Armbruster. You see him here together with Hans Specht at the beamline. And now, what did he measure? He looked for X-rays when fission fragments impinge on various materials. So what you see here is the cross-section for ionization as a function of the proton number of the target atom. And you see for the light and heavy fission fragments, there are peculiar results. You would normally expect that you get just a linear rise in this plot here for the ionization cross-section, but there were some bumps here. And they were so surprising that in his PhD examinations, the examiner started to discuss among themselves what the origin is, thereby forgetting to ask him serious questions. And well, he himself, Hans Specht, gave an explanation which was later confirmed in other experiments. What he saw were quasi-molecular X-rays. And that is illustrated here on this side. You see two atoms approaching each other in the center of mass system. The motion of the nuclei is much slower than that of the electrons. And so for a short time, the electrons will see the combined charge of both atoms, Za plus Zb, and intershell ionizations that occur in this collision at this time will then lead to molecular X-rays. And you see, this is a field that was completely unknown. And in his PhD work, Hans Specht already opened up a new research field, namely to study quasi-molecules formed in adiabatic heavy ion collisions. And that was pursued by many groups hereafter, after this first work. All over the world, in all tandem accelerators, you find atomic physicists who were studying these quasi-molecular X-rays. And he himself took this field up again later at the MPE Heidelberg tandem when working together with Reinhard Schuch and Rosmet Böcking and their collaborators. Now, the second step in his career was the time he spent in Canada, very cold Canada, as he mentioned. And what was the topic at that time that was exciting people, namely the possible existence of a double-hump fission barrier. Sergei Polikarpov and his collaborators discovered so-called fission isomers in 1961. These are excited nuclear states that decay by spontaneous fission, but with half-lives in the millisecond to nanosecond range, which is of course much shorter than the lifetime for fission from the ground state. And a possible explanation for these states was given by Willem Stotinsky, who said, well, these fission isomers are states in the second minimum of the fission barrier, and that results from the superposition of shell effects that you see here plotted as a function of deformation on top of the liquid drop model fission barrier, which is determined by the interplay between Coulomb repulsion among protons and the surface tension that tries to keep nuclei spherical. And so the existence of this second minimum, that was what Hans interested, and there were no experimental evidences apart from the fact that you have found fission isomers. But let's look at the structure of this barrier, and that was his idea that he followed up. What you see here is important for the subsequent discussions. The shell effects that are superimposed on the liquid drop model barrier show a particular dependence on deformation. Shell effects are not only are reflected by these gaps at spherical deformation or zero deformation, but you see them as well here for particular deformations of the order of C over A or even C over A equal 3 or 2. And that was the idea that when you have deformations of this size, then you will get strong shell effects which lead to the production of these fission isomers. Now, how can you do this? Here you see the double hump fission barrier in a schematic way displayed. What you see is if there is such a second minimum in the fission barrier, what would you expect? You would expect that there are vibrational states in the second minimum which serve as doorway states to fission, because from this excitation energy you have only a very small barrier to penetrate, and so there will be enhanced fission probabilities for these states as an evidence for the existence of a double hump fission barrier. And this he measured. Here you see the spectrum, and here you see structures which correspond to these states with enhanced fission probability. But how did he measure that? You have a beam coming in here, you have fission detectors positioned around the target, and here you see the focal plane of a magnet where he installed a gas detector. Now that was a technological innovation, because at that time it was standard that photoemulsions are placed here in the focal plane of magnets, and then these had later to be scanned by the scanning girls. But with those you can't do a coincidence experiment. So it was essential that he positioned a gas detector here in the focal plane, because then the protons could give you the excitation energy which you need for making this plot here. So that was the first indication for this idea, do something new by seeing and then see something new. Really an innovation at that time. Many other Büchner magnet spectroscopists then also turned to gas detectors instead of emulsions. Well, here you see Joachim Specht assembling his position-sensitive detector, and you see here he's looking for new results from the experiment together with his hosts, Milton and Fraser. And this is the most modern computer at that time, a VAX. I remember myself, that was really a huge thing to have a VAX. Yeah, so that was the time in Canada, but fission isomers still interested him, or the existence of the double hump fission barrier. But he came back with the idea, somehow I should try to measure the deformation of these states. The characteristic feature of a deformed state is that there are rotational bands based on the lowest state in the minimum. So if there is such a second minimum, one should also have a rotational band based on the fission isomeric state. And then you look for the rotational transitions in coincidence with delayed fission in order to prove that there is a rotational band. And then you can measure the moment of inertia given by this formula here. E is the energy of the rotational states, I is the spin, and the larger the deformation, the larger is the moment of inertia, the smaller are the transition energies, and this was the idea, to measure the moment of inertia and compare it to the first minimum. Now these transitions are so low in energy that they do not occur by gamma emission, but rather by the emission of conversion electrons. And what you see here is the spectrum that made him famous. What you see here are conversion electron lines, L1, L2, Mn, for the 4 to 2 plus transition, the 6 to 4 plus transition, 8 to 6 plus transition. But you see at the same time, this spectrum was a fight with statistics. And when you read his biography, he reminds us, as soon as the first signs of some electron lines came up in the experiment, he gave, as he said, an unforgettable speech at Munich to convince his colleagues that he needed at least several times the amount of beam time that was actually granted for that experiment. And he convinced them, and he succeeded. And this spectrum really made him famous worldwide, as I said. He got a lot of invitations for talks. When you analyze the spectrum, you find that the moment of inertia is much larger than that of the ground state, and it is even larger than the moment of inertia of a rigid rotor. And so what Hans Specht has proven with this experiment is that fission isomers are really shape isomers. And that was long before the time when gamma spectroscopists took up the study of shape isomers, where they did beautiful experiments in the rare earth region showing identifying rotational bands up to even spins of 40 plus. But he was the first to show that shape isomerism exists in nuclei. Now, the next question, however, is, here we see the Munich tandem where the experiment was performed. And here we see Hans Specht at that time, together with his counterpart from the Technical University, Ewald Konechny. Both of them, they were the senior scientists in this experiment. As I said, due to this success with this measurement, Hans Specht got a lot of offers. But the Heidelberg people were reluctant. They said, well, maybe he's a good experimentalist, but he can't really give lectures. So let's test that. And indeed, it was tested. Here we see Hans Specht giving his test lecture in Experimental Physics 1 in the winter term 1972-1973. Yeah, now, still the question was, how big really is the deformation? What Hans Specht had shown, first of all, a rotational band exists on top of the fission isomeric state, and the moment of inertia is larger than that of the ground state. But how large is the deformation? Is it really 2 to 1, as we would expect from the theory arguments? Well, the answer to that was given in Heidelberg. I had done my PhD work at the Max Planck Institute for Kernphysik, also working on fission isomers, hot topic at that time, really, under the supervision of Peter von Brentano. And we had discovered several fission isomeric states in actinide nuclei. And then I spent 2 years at the Niels Bohr Institute, where we worked together with Sven Björnholm and Geir Sletten, and we discovered many more fission isomeric states and were able to establish some lifetime systematics. And then I returned to Heidelberg in 1973, just at about the same time as Hans Specht had accepted his professorship here. And so we were both interested in fission isomers, so we joined forces. And the third very important person in this game is Dietrich Harrach. I'm sorry, Dieter Habs, I'm sorry. Well, what was the idea? We wanted to really measure the deformation, not only show that it is larger than the ground state, we wanted to measure the quadrupole moment, and you can do that by measuring the lifetimes of these rotational states that Hans Specht had discovered in this Munich experiment, because the lifetime is related to the quadrupole moment. Here's the energy, which you anyway measure, and so from the quadrupole moment you can directly deduce the deformation. Now, when you have seen that these rotational transitions are low in energy, so they occur by conversion electrons. But what happens now if you have an atom with a nucleus in the second minimum, and you populate the fission isomeric states? Then these rotational transitions occur, and whenever there is a rotational transition, you will create holes in the inner shells of the atom due to the conversion electron emission. And these holes are then filled by Auger cascades. That means there are electrons emitted for each rotational transition. You emit on the order of 8 to 10 electrons. And if you now have a population of the fission isomeric state by several rotational transitions, and each transition produces charge states of 8 or 10, then you will get a charge distribution like this, reaching up to 50 plus. We could demonstrate that experimentally by producing fission isomers, which are then recoiling from the target. They are deflected depending on their charge state, and they are then detected here in detector foils in this detector system. And in this way, it was possible to verify that indeed you change the atomic charge state when there is a rotational transition in the second minimum. And now Dietrich Habs comes in. He had an extremely clever idea. Namely, when you have a rotational transition occurring before you reach a carbon foil, then the high charge state can be recovered, can be compensated by electrons that you pick up by passing the carbon foil. The average charge of these recoils is of the order of 2 plus, because of the very low recoil velocity of 0.2%, velocity of light. But now, when you have a transition, and that is the trick, that occurs after passing the carbon foil, then you will see a high charge state. And so by moving this carbon foil in distances of the order of a few micrometers to several 10 micrometers, we were able to really follow up the de-excitation of the rotational band and thereby measure the lifetimes of these rotational states that Hans Specht had discovered before. And here's the result that we obtained with the so-called charge plunger technique. I guess the name is now explained why it is called charge plunger technique. You see here the quadrupole moments as a function of the mass number, and these are the fission isomeric states where we determine quadrupole moments. And indeed, the deformation that you get out from quadrupole moments of 36 plus minus 4 bar is indeed 2.0 plus minus 0.1. So these are really the shape isomers that Wieland-Sotinsky really predicted. Well, this was not the only thing that Hans Specht was interested in, and now we come to Dietrich von Harrach. At that time, there was another field which interested people a lot, namely deeply inelastic collisions between heavy ions. And the options provided by the UNILAG at GSI had gone into operation, was founded in 1970. So there were new research options, and Hans Specht recognized that immediately to study really these collisions of very heavy nuclei up to uranium and uranium, of course, hoping to find super heavy elements in this way by mass transfer between two heavy colliding nuclei. And in order to do that, you cannot really work with tiny silicon detectors, which was the standard at that time. And so, following the advice given by his thesis advisor, do something new, and then you will see something new. He insisted that square meter size detectors are built, which can be operated in the Heidelberg Fass, as was it called, at GSI. You see here these huge detectors, and that was the playground of Dietrich von Harach and Peter Glessel. And this detector system allowed to measure kinematically complete reactions where there are 3 or 4 particles in the final state. So that again was a breakthrough. Don't use silicon detectors, use square meter gas detectors. Again, an innovation. And they produced very interesting papers here. And just to mention one of them was the angular momentum transfer, deeply inelastic collisions. Sorry. And this work was followed up by many other collision systems that were studied in this detector setup. But there was also another important measurement, namely the direct observation of Coulomb fission. This was done in a different setup, but also here at GSI, using tungsten beams. We could show in those collisions between, tungsten and uranium, very peripheral ones where you had no nuclear contact, but only the Coulomb force was acting. And that was a system that was developed by Hartmut Backe, some electron spectrometer on a solenoidal basis. That was also another important step and first result from the UNILAC here at GSI. Yeah, here you see the team of Hans working with him in Heidelberg. Here you see Dietrich von Harach, whom you will hear later. This is Peter Glessel, Jürgen Schuhkraft. This is Dieter Habs, and this is myself in the young days. Yeah, but Hans Specht wasn't only interested in heavy ion collisions at GSI energies. Why not go for very high energies, very much increased energies, namely to look for the quark-gluon plasma at CERN? That was his new project he wanted to pursue, and we will hear more about this from Axel Drees. Because he worked with Hans Specht on the Ceres experiment. He did his PhD with Hans Specht in Heidelberg. He then went to Stony Brook and continued the research in heavy ion collisions there with the Phoenix detector and the S-Phoenix detector. And he was among the people who really found the jet quenching in heavy ion collisions. And he is now a distinguished professor in Stony Brook and still active, as I heard. Okay, Axel, it's your turn. Now we will see how we manage to pass the microphone on.
It's my real pleasure to be here today. And I would actually not be here today talking to you if I would not have been exactly at the right place 40 years ago. I was a student in Bonn, and I was not interested in nuclear physics. But on that day, I was at a conference together with Hans Specht. And his talk about the future heavy ion program at CERN and the Helios experiment was so fascinating that I decided on the spot I will go to Heidelberg and learn from Hans Specht. So I became his doctoral student. He became my advisor and mentor. And I continued to follow him on a passionate yet relentless pursuit of science for 12 years. So what I will do today, so it's a real honor for me to give this tribute to Hans Specht here today. And I will take you on a tour starting from the early days of heavy ions at CERN, take you on the roller coaster ride with Ceres that leads then to the NA60 experiment, which led to establishing the fingerprint of the quark-gluon plasma, the thermal fingerprint of the quark-gluon plasma. So I'll start with the development, the evolution of the universe, starting from the Big Bang to today, 15 billion years. This is a logarithmic scale to blow out the early development. So after a short formation time, we believe that the universe expanded adiabatically in a Hubble expansion, cooled down, and underwent various phase transitions early on that changed the appearance of matter to what it is today. And what is of particular importance to us here is this QCD phase transition that happened about 10 microseconds after the Big Bang at an unimaginably high temperature of 2 times 10 to the 12 degrees, or in units we use 160 MeV. Before this transition, the universe was mostly made out of gluons and quarks that roamed around freely, the quarks having only a very small mass from the Higgs mechanism. But then as they transitioned, as they went through this transition, they were confined into hadrons, and symmetries were broken, in particular the chiral symmetry, which gave them a very heavy mass. The idea of heavy ion physics is to use heavy ion collisions to recreate this state of matter and then observe how hadrons are formed and learn something about their fundamental and not completely understood properties. So what you will see on the next slide is an evolution of a heavy ion collision. So you have the collision here. We believe that likely there is immediately a highly entangled quantum state created that leads to a thermalized quark-gluon plasma that then also expands like a Hubble expansion, cools down, transitions to hadrons which continue to interact until they stop interacting, stream freely, and long after the collision decay into other particles. Now throughout the collision here, electromagnetic radiation is emitted in forms of photons and in forms of virtual photons that appear in nature as electron pairs or as electron-positron pairs or muon pairs. And they carry information about what happens here, rich information to the detector, including what the temperature was and its development, the radial expansion, the expansion of the system, and much more. That is the thermal fingerprint of the quark-gluon plasma. Now, Hans Specht early on realized this and focused very much on the discovery potential of this, that these measuring thermal radiation would offer. So during his sabbatical, when he started his career at CERN in 1883, he was responsible for a Cherenkov detector that was added to the axial field spectrometer. Here's a picture of it. Here's a schematic of the experiment. And this would be used to measure electrons and positrons. I have here a plot from the time where I believe Hans Specht compiled all the existing data. This is a mass distribution. You'll see many more of those, so I'll explain it once slowly. What is plotted here is the yield of electron-positron pairs normalized to the number of produced particle as a function of mass. And you see here these resonance structures. Those are vector mesons that decay directly into E plus, E minus, show up in the spectrum, and that sits on a continuum. And there was quite some excitement initially about this continuum at very low masses. It then later turned out that really it was an incomplete understanding of the hadron decay sources that led to this continuum, and that it would be more complicated to find the thermal fingerprint. When the ISR was switched off, the heavy ion program at the SBS, Fixed Target Heavy Ion program, began. And Hans was one of the spokespersons, as Volker already mentioned, the Helios experiment, one of the first generation experiments. This is also when I joined his group. So this is a layout of the Helios experiment. I won't try to explain it all to you. This is a muon spectrometer, a calorimeter down here, and then the detector system that the Heidelberg group was mostly involved with was this, what we called at the time the external spectrometer. It allowed to measure photons through photon conversions and charged particles. And the picture here is from the day when I and my fellow student Hans-Werner Bartels defended our PhD thesis. And from our work, we set the first upper limit at the time on thermal photon production in heavy ion collisions. It would then take many years, decades, before a real signal was discovered by later experiments. Hans had from the get-go the plan to use this space here to put in a device that would allow to measure electron-positron pairs. Now, not everybody in the collaboration was interested in that, and even those who were interested did not believe that it would be possible. So the collaboration split ways, and CERS was born. So, in my opinion, CERS is his masterpiece of experimental work. So I put here together, it was planned, meticulous over years on hundreds of pages of handwritten notes, and that then led to a proposal that was submitted in 1988 in the summer. This is the cover sheet of the proposals. It had 24 authors. I was one of the older ones at the time, was a really young team, was Hans Specht's group, Peter Wurm's group from the Max Planck Institute in Heidelberg, and Itzhak Zerouia's group at the Weizmann Institute in Israel. What I've shown here is this timetable. This is an actual figure from the addendum to the proposal, and it lays out how we would construct the thing in 1 year and then start taking physics data. Now, as I had told you already, most people in the field did not believe that this was possible or could be done. Hans, however, was absolutely certain that it could be done. And he had great faith and confidence in his group, which inspired us, and we were young and enthusiastic, and it somehow happened. So I will explain the experimental setup and then guide you through the roller coaster ride that we embarked on. So it was a cutting-edge technology experiment and very streamlined. I could have also said a very minimalistic approach. So the key component was to have a hadron blind detector that would not see all of the particles produced, but just the particles of interest. And detector technology of choice was the ring imaging Cherenkov counter technology, a concept that was just developed 10 years earlier. There was no feasibility demonstrated yet at the point. There was one other big experiment that was trying this technology, but their detectors weren't working yet, and it would take them still a number of years to get working. Almost everything else in the detector was either cutting edge or rather modern technologies. I'll just rattle off a few things. We had a carbon fiber mirror here. We had superconducting magnets, sophisticated field shaping, silicon detectors, multiprocessor second-level triggers, 120,000 readout channels back then, which was quite a lot, and so on. In 1990, we added redundancy in the tracking by adding one space point with a detector technology that was just proposed a couple of years earlier, a silicon drift detector. So here I put together a collage of pictures that start with the delivery of components at CERN and then lead all the way to final preparations for taking data just 1 year later. So you'll see Hans is in many of these pictures. Here's a picture of the young team. One of the pictures that I like in particular is this one because it has Hans Specht here, Peter Wurm, and Itzhak Tsuruya all together in the pit getting ready for the experiment. And we did take data, not with all of the electronics, but just with a fraction. You see here, this is from our progress report to CERN. These are ring images in the first detector that then get bent open by the magnetic field in the second detector. They had about the right number of photons that were expected for this detector. We were the first to achieve that, and they had the right resolution. So we were very happy about that, but not all was well. So we had a parallel plate amplification scheme here for the UV photons, for the Cherenkov photons, and that did not work. It was sparking like crazy. It would not hold the gain that was needed to detect the individual photons, even though the detector was gated. It would spark every event. And then it would need to recover, and that would lead to a data taking rate of about 1 hertz. And it would kill the electronics. So it was absolutely unacceptable. So we spent about a year to figure out what was causing this. Turned out that it was the neutron flow that just came with the interactions that we were producing, so it was inherent to the experiment. We found a workaround, which was introducing a wire amplification here at the last stage, which was self-quenching and stabilized the detector system. And it had the advantage it didn't need any high voltage gating, which was a pain in and of itself at the time. We also, in that year, beefed up our electronics and added diode protection to all the 120,000 channels, 60,000 channels of which the diodes were soldered in by hand by us. And the other electronic needed to be completely replaced. This is one of the things we wrote down, the ordeal we had, and a sentence that just could not be removed from the conclusion. The paper ends with Hans's quote, "We will in all future stick to the lovely tolerance of multi-wire proportional chambers," and at least I have so far. Okay, so now we were ready to take data, and that's what you see here. In 1992, we took sulfur gold data. This is an event display picture of an event in the first UV detector, in the second UV detectors. Those are the Cherenkov ring images. You can see here the silicon detector and the silicon pad detector. When I say screenshot here, it literally means you take a camera and you photograph the screen at the time. There's sort of an interesting detail here. There's this next symbol, which was the state-of-the-art computer. It had state-of-the-art graphics at the time, and we were connected to the first ever commissioned web browser that was just put in operation a year or so before we got this computer at CERN. In the meantime, while we were accumulating data, Hans convinced, he was always on the lookout to improve things and make them better. So he had convinced Volker to bring his calorimeter tabs to CERN and stack it all up behind Ceres and join us for the next year running campaign of proton collisions, proton beryllium and proton gold collisions. And this was in a way the stepping stone to the scientific breakthrough for Ceres. So here are again some mass spectra. You see here on the left, proton beryllium, proton gold. The data is well described by this cocktail of hadron decay sources with quite good precision. This was possible by directly measuring these hadron decay contributions with the TAPS combination of the TAPS calorimeter and the electron pair spectrometer. But when you go to sulfur gold collisions, you see that there's a significant enhancement above this. This was the first indication, and in hindsight, the discovery of thermal dileptons at CERN. The paper that was written to date is still the paper from the SPS heavy ion era that has the highest number of citations. It triggered a huge development in theory, hundreds of publications, and I'll say a little bit about that in just a moment. Now, we were taking data with proton beam in '93. We were extremely happy when Hans informed us that, well, before the end of the year, we have to submit a proposal to CERN to continue data taking with lead beams. He somehow managed to convince us to do this. So we submitted a proposal in January. It added redundant tracking to Ceres, which meant at the time we now had 2 space points in front of the first ridge and 1 space point behind. Many of my colleagues today don't believe that you can track with 3 points, but you in fact can, and we did. So we spent 94 to update the detector system with these detectors, get them ready for data taking, and then measure a couple of days with lead beam to demonstrate the performance, because people at CERN were kind of skeptical whether this would work. It worked much, much better than we had expected. So we then were approved for beam times in 95 and 96, which were the main production beam times with Ceres in the early lead era. So we had just taken data 1995. The beam times are typically towards the fall, when we were reminded that we were organizing Quark Meta, the biggest conference in our field, the next year, in 6 months from now. Now, it was absolutely unthinkable to any one of us that we would not have first results at Quark Meta. So we were with the back against the wall, and this time we really needed a miracle. Okay? So what did we do? We said, well, if we could just modernize our code and get away from Fortran and rewrite everything in C++, then it would be just fine. We ended up having 5 days spare to prepare our talks for Quark Meta. This is sort of a photocopy of the preliminary data set that was shown at Quark Meta. Here on the next slide, I show you the final result. It's again a mass spectrum, combined data from 95 and 96. You see the data points. It's compared to the sum of the cocktail of all the sources. In addition to that, there's a contribution from the hot hadron gas, pion annihilation through the rho meson into electron-positron pairs. Clearly that was necessary, and furthermore, it wasn't just, this intermediate row here was not just having vacuum properties but it had to be modified in the medium. There were competing theoretical approaches at the time that either the mass could drop as chiral symmetry would be restored, or the row could just melt and broaden away. And at the time, we did not have the statistics and resolution power to resolve that. There was a final push to upgrade CERES to improve the mass resolution by adding a TPC behind the setup. That was led by Johanna Stachel, who had just joined Heidelberg, but more or less Hans was no longer really involved in that part. Nonetheless, data that was taken in 1999 led at much lower beam energy, which translates into much larger baryon density. That led to the final PhD thesis that Hans supervised. Now, around that time, Hans was closing in on retirement. However, he was not going to slow down. So he actually joined a new experiment, the Na60 experiment, and inspired a whole new team with his passionate and relentless approach to science. So Na60 is a state-of-the-art experiment, dimuon experiment. It was built around a battle-hardened muon spectrometer, which has an absorber here to stop the pions and kaons, a magnet with muon detection chambers in front and back to measure the pairs, and then a triggering system. This new setup added a target spectrometer here with state-of-the-art silicon detectors. These were silicon pixel detectors that were designed for the ALICE experiment and would then be used also in the ALICE experiment. And that really, really improved the measurement in several ways. For one, it much improved the mass resolution. You see that here on this figure. This is the spectrum, the dimuon spectrum, just measured by the muon spectrometer. And that then turns into this with much sharpened structures by using this information from the silicon detectors. At the same time, the background here that comes mostly from kaon decays was significantly reduced. Also, it turned out, although it wasn't designed that way, that the acceptance for this thermal region was much larger, opened up much larger. And maybe the most important part is that it added the capability to distinguish between prompt muon pairs that were of thermal origin and muon pairs that were from heavy flavor decay by measuring the displaced vertex of the weak decay of heavy flavor. In 2005, the first data was officially shown at Quark Meta in Budapest, but Hans Specht gave us a sneak preview 2 months earlier at a workshop in Trento. And here's a picture of that workshop. Here's Hans. And then these workshops, I'll say a little bit more at the very end, are a little bit of who is who of this particular subfield of measuring thermal radiations and dileptons. These are his original slides. He did not talk on behalf of the Na60 collaboration, but on behalf of himself. This is the result. I show here the finally published one. You will not really see much difference. And now, different from what I have shown you earlier with the CERES result, all of the hadron contributions, decay contributions, are subtracted here. So this is just the thermal contribution and the rho meson. And at the time, there were these two competing theories of how the rho would be modified in medium. Either the mass would be dropping or it would just melt away. and clearly only one of them is consistent with the data. That settled some 10 years of theoretical dispute. Now, once you have the thermal contribution isolated, you can correct that for all detector efficiencies and such, and absolutely normalize it. And that then leads to the thermal fingerprint of the quark-gluon plasma. So what you see here is again the mass distribution. Now it's just the thermal part. Those are the red points as a function of mass. And then there are various theoretical calculations that were available at the time. In the low mass part, let's say below 1 GeV, it's dominated by the rho, which melts in the QGP or in the hadron gas, and we just discussed that on the previous slide. Above that, there's an almost exponential spectrum that you can fit, and that fit has one parameter, which is the temperature of the system. And depending on where you fit this, you get values around 200 MeV, well above the transition temperature from hadronic matter to partonic matter. Now, one can also look at the momentum distributions of these dileptons. The momentum distributions are also exponential distributions. However, the slope parameter captures both the temperature and the radial expansion that blue shifts the radiation that is emitted from the source. So what is shown here is the effective temperature as a function of mass. And you see here this rising trend, which is the telltale of a radial expansion where every particle, everything rides on a wave pushing momenta of different masses, so it's a velocity wave, and therefore creates this mass dependence. Now at 1 GeV, this drops and becomes a constant value of 200, which can be interpreted as that at SPS energies, you create a quark-gluon plasma. It's the same temperature value, but the quark-gluon plasma itself does not really expand yet. It's really all the expansion comes in the hadronic phase. This is a solid proof that quark-gluon plasma is formed at the SPS. This is still an exciting field of research. Actually, at any major conference in the field, you will see new results. I'll just give you a flavor here. I won't go through them. This is from earlier this year, March, from the Quark Meta meeting in Frankfurt. Results from many experiments over a large beam energy range or temperature going from here to here, or baryon density going the other way. GSIS Hades, the RIC experiments, Phoenix and Star, and Alice. So it's a vibrant, remains a vibrant field with many new results, and there are actually new detector systems planned or in various states of readiness, including CBM here at the ZIS 100, the Alice 3 upgrade, which hopefully we will see for Run 4, and then the NA60 Plus experiment. And I want to spend one more short moment on the NA60 Plus experiment, because that does have Hans Specht's fingerprints on it. So after NA60 stopped data taking, Hans and a very small group of his collaborators started to immediately plan the next generation experiment. It looks very much like NA60. You can think of it as a super NA60. It has the same kind of setup, a magnet, a muon system here with the yellow ones are muon chambers, a magnet in the middle, absorber to measure muon pairs, and then a vertex spectrometer with silicon detectors. Now this is all brand new equipment and optimized to measure the largest system at the CERN SPS at the highest energy down to the lowest energy to explore the effect of the changing baryon density. And the projections are that this will have 10 times more statistics than Na60 with real new discovery potential. I give here one example from the proposal. This is the mass distribution similar to what I've just shown you. And in this region, you're sensitive to various effects of chiral symmetry restoration. Okay, so the proposal has been submitted in May, and we expect that it's going to be approved imminently in November. So one fun fact of this, it brings sort of Hans' involvement in dileptons at CERN full circle, because this experiment will be set up at the H8 beamline at CERN some 20 years, or 40 years after Ceres was built at exactly the same location. Okay, so I want to wrap up by just recalling the encounters I had with Hans Specht at these Trento meetings. After I left Heidelberg, this would be a place where guaranteed I would run into Hans Specht. From the first meeting here in 1999, this is Hans right in the middle, through the years. The last time he participated in person was in 2018. Interestingly, I was informed by the organizers that they had to change the reservation of my hotel because they just had learned that I was his designated driver. I had not yet heard about that. In 2021, he did participate by Zoom. But then, of course, the last one that just happened, he was not there, but many of the talks were dedicated to him. I know he would be impatiently waiting for one of the next ones to see the first results from Na60+. And I assure you, he will be missed there. Thank you.
Let us come to another important step in Hans Specht's life and in the life of GSI, namely his years as managing director of GSI. Thank you. So, GSI was founded in 1970, and the founding director was here, Christoph Schmelzer. Then the next director was Gisbert zu Putlitz, and this was Paul Kienle. And here we have Hans Specht, now director for 1992 to 1999. Now, Hans Specht introduced various changes when he came here. The first thing was he changed the management structure in the sense that he introduced the 6-member directory board. Namely, he is the chair and scientific director. He appointed me from Gießen to be the research director, and this position was then taken over by Jürgen Kluge in 1999. Norbert Angert became the accelerator director, and the scientific and technical infrastructure was then covered by Wolfgang Grün from CERN. And the administrative Geschäftsführer was Helmut Zeitträger, and not to forget, important scientific secretary Klaus-Dieter Groß. As you see, he insisted that people from outside join the directorate of GSI. We had various meetings, of course, in the directorate, but all the leading scientists of GSI were mostly involved in all these directorate meetings: Peter Armbruster, Rudolf Bock, Jürgen Kluge, Eckhard Grosse, Uli Lien, and then later also Peter Braun-Munzinger. But there were also roundtable discussions with younger colleagues, and we were talking at round tables on daily matters. But another important change was the internationalization of the Scientific Advisory Board. English was introduced as the official language. So we could get advice from all over the world for the work at GSI. Now, the extension of the GSI facility, here was the UNILAG, the extension by the CIS synchrotron and by the experimental storage ring had gotten into operation under the directorship of Paul Kienle. New detectors were introduced: fragment separator, Aladdin, FOPI, Chaos, and TAPS. And this was really an interesting time, because the new research options that were provided by this facility were really pursued with a spirit of great enthusiasm. And just to show you some of the results that were quite important, and I assure you it was an extremely euphoric and scientifically exciting time with numerous results. And just to list a few of them: the synthesis, identification, and study of exotic doubly magic nuclei, mass measurements of many exotic nuclei, either with the Schottky technique or the time-of-flight technique in the fragment separator ESR combination. Then first observation of bound state beta decay in osmium, first observation of low-lying 1s pionic states in lead atoms at the fragment separator, evidence for the liquid-gas transition in hadronic matter in the Aladdin, and observation of collective flow in gold-on-gold collisions at FOPI, evidence for medium modification of kaons and dense matter at the chaos spectrometer, first detection of neutral mesons in heavy ion collisions in the GeV energy range with TAPS, and precision QED studies in strong electric and magnetic fields. So these were all new results that came in, and you have to imagine all the commissioning of the detectors were done starting with the inauguration in 1990, but Joachim Specht came in 92. This new research program really took up pace. But of course, the particular highlight was the discovery of super heavy elements. There was already a campaign in 1982 up to 1984 where the group headed by the campaign was headed by Gottfried Münzenberg, but the group was around Peter Armbruster, and they discovered bohrium, hassium, and manerium. And then 10 years later, after an upgrade of the ship spectrometer, and the group then the activity headed by Sigurd Hoffmann discovered the elements 110 to 112. And we see here all the leading figures, worldwide leading figures in super heavy research, together with Peter Armbruster. This photo is taken at the farewell ceremony for him in 1996. Here we have Nobel Prize winner Glenn T. Seaborg and Yuri Oganessian from Dubna, and Specht welcoming them here. Now, these successes that were achieved were, of course, celebrated, in particular in the 25 years anniversary of GSI, where Hans Specht, you see him here, addressing a large audience of politicians and well-known scientists from all over the world. But despite of all these successes, Hans Specht felt we still have to go a step further. Again, do something new to see something new. And indeed, in 1994, the directorate accepted the proposal of the HARDES collaboration to build a high acceptance dielectron spectrometer. And in the same year, we decided that GSI will officially participate in the CERN heavy ion program by building the lead injector and also participating in the building of the ALICE detector. And I guess you are all aware how what an enormous scientific output these two detector systems have provided in the long run, and how important it was to take these decisions back in 1994. Now, as soon as Hans Specht took office here, he realized the high potential of GSI in the field of applied physics, in particular using heavy ion beams, for instance, together with lasers, capabilities that you find nowhere else in the world. So he really pushed this very strong, and these are the two projects that were very close to his heart, namely the petawatt high energy laser for the heavy ion experiments. It's a unique combination of high intensity heavy ion beams with lasers to study the better at extreme temperatures, pressures in plasma physics, astrophysics, and in energy research. So the project proposal was submitted in 1998, and the groundbreaking ceremony, which you see here, was then in 2020, after Walter Henning had already taken over as managing director, but Hans Specht, as the person who pushed the whole project, he was, of course, present. And then the other very important applied physics project was the heavy ion cancer therapy pilot project at GSI. As you will hear in more details in a moment, this was the very first attempt to use heavy ion beams in cancer therapy. And this pilot project, 450 patients were treated, and the project then led to a project proposal in 1998 to build the the Heidelberg Ion Therapy Center. And who else should give the talk about this? It is, of course, Jürgen Debus. He was the medical responsible project leader of this pilot study, and he is now director of the Heidelberg Ion Therapy Center. He is also professor, of course, at Heidelberg, and he is someone who did two studies. He studied physics and medicine, and he did his examination with Hans Specht. That means something. And so we are very glad to have him here. Jürgen Debus, please come up and give us your presentation.
To work together with Hans Specht was always for me a great pleasure. As I said, this was also very challenging because he questions irrational arguments. So you have to reason your arguments very well in order to be accepted. And this was, in that sense, an excellent teacher for me, but also for countless students which had been inspired by him. So may his example continue to guide us. Also, basically, his relentless work, not accepting borders or limits, rather than to go ahead and challenge with limits and with borders. I think this is one of the key aspects in order to get to new insights. And may his legacy endure, not only in the annals of science, but also in our minds and hearts, and all of us who try to follow him in his ideas. Thank you so much.
Remembering Hans Specht. Today we are remembering Werk und Wirkung of Hans Specht, meaning achievements and impact of an outstanding natural philosopher and scientist. I'm grateful to the previous speakers of today's colloquium having provided ample evidence for that. Do we grasp and understand sources and resources of vision, vigor, and relentless dynamics characterizing Hans Specht? Do we understand the deep and lasting impression Hans Specht made on those having discussed and interacted with him in collaboration panels and committees? This is witnessed by the many outstanding scientists from all over the world having contributed to the memorial book, praising his exceptional intellectual and communicative skills and his contributions to the advance of science. I had a first opportunity to reflect on this on the occasion of his 80th birthday, when he himself asked me, bisschen weiter weg. So ist es. Ist das besser? when he himself asked me to give a kind of overview over his origins, career, and achieved accomplishments. At that time, I tried to understand and interpret Hans Specht as an incarnation of Protestant ethics and existential philosophy, providing the grounds for the emergence of an authentic, charismatic, natural scientist and philosopher, deeply committed to facts and reality, seeking for truth and enlightenment. This perspective prevails in my written contribution to the memorial book with the title Spechtia, trying to relate episodes of his career to the authentic, charismatic, and dynamical leader which Hans Specht was. Repeating this exercise within the time frame of 25 minutes, I consider to use Hans Specht's words as Zeitverschwendung, a waste of time. This verdict on an idea many of us having discussed with Hans Specht, may have heard many times. It meant to not dive into dead-ended or circular path of thoughts and ideas, which he had already explored and concluded to be of such quality. The antithese to Zeitverschwendung is geradeaus denken, straightforward thinking, avoiding the aforementioned traps and detours. This straightforward thinking, many of us, having discussed with Hans Specht, also may have heard repeatedly. To me, it even appears as a kind of leitmotif in Hans Specht's way of approaching challenges of nature and society. So it might be worth to have a closer look. These days, it is impossible to reflect on geradeausdenken, which is a phenomenon of human intelligence, without alluding to its artificial counterpart. This immediately touches on a narzisstische Kränkung, which is a narcissistic injury, according to Freud, which it would be if the fantasies of an artificial general intelligence would become true. There's even the daunting project of the divergence, when humans will stand as decorations at the sideline. I myself do not fear such a scenario, and I put my money on Roger Penrose, denying the possibility of that humiliation, so I'm not impartial, but of course one should keep an eye on it. Back to Hans Specht and the human intelligence. Trying geradeausdenken myself, we are immediately in general relativity, where geradeaus is determined by all the kinks and curvatures of the dynamical space-time. It's definitely not mit dem Kopf durch die Wand, meaning bull-headed, inflexible, ignoring advice and realities. Quite opposite. If there is a vision of the goal, then proceeding on the geodesy minimizes Zeitverschwendung. It is rather what is termed in cognitive science as fluid or expansive intelligence. Here to me to be a striking match with what I and many colleagues have experienced interacting with Hans Specht. Going into detail, fluid intelligence means dynamically alternating and quasi-parallelizing divergent and convergent cognitive phases. The divergent phases are those extending the view and fully access the associative English is difficult for me, landscape, producing fantasies, hypotheses, and visions, and sometimes hallucinations. The convergent phases instead operate as reality checks, seeking experimental or observational confirmation, cross-checking inspirations with all facets of reality, sorting out the hallucinations. Making it clear, it means checking against all aspects and sensations of reality, defining the boundary conditions on our fantasies. The dynamic of this fluid and expansive thinking appears to be largely driven by the self-enhancing dopaminergic mechanism. I will come back to this somewhat outlandish term, since it helped me to approach and possibly understand some aspects of Hans Specht's preferences and motives, in particular those related to music, sports cars, skiing, and others. But let's dwell for the moment on vision and hallucinations. More recently, hallucinations have been realized as a threat to the usefulness of large language models for decision making. Some researchers believe that hallucinations are a good thing to simulate their badly missing creativity. But the majority of experts is frightened, since it undermines the credibility of AI. And the dream of general superintelligence may melt away. AI hallucinations are found more and more frequently, since the databases are incomplete, biased, or even corrupted. This appears to become a real problem for AI, especially if AI learns from AI. A vicious circle. It's here where we observe the emergence of narratives explaining causes and effects which might be partially or entirely hallucinatory. While we may want to think that natural science is unaffected, we are witnessing this kind of majority vote physics gaining terrain. Should we really believe in multiverses, Big Bang, inflation, dark matter, supersymmetry? This morning, I took up my Frankfurter Rundschau and I read that dark matter is probably a fake or a myth. Well, I knew that since some time, but now even Frankfurter Rundschau writes on the first page. Again, it was a highly authentic Roger Penrose in his book Fashion, Faith and Fantasy, spelling out these doubts. This brings me back to the earthbound, authentic and fluid intelligence of Hans Specht. Does it really explain the deep impression he made on us participating in conferences, collaboration meetings, panel discussions, and in particular as a convener or chairman of committees? There was this calm and self-confident, somewhat minimalistic, but nevertheless eloquent and witty language, arguing and explaining things and situations. This cool, impartial approach made him a highly respected, trustworthy, and much sought-for moderator, taking the heat out of the arguments, aiming and arriving at constructive solutions. Of course, this needs the authentic, resourceful, and fluid thinker, but it needs more. Something I would loosely describe as a social intelligence, with a quick grasp of personalities, their intentions, and their interactions. Never loud or aggressive, he could finally get a grip on everyone accessible to well-founded arguments. It was nice to have Hans Specht on his side, but it maybe sometimes have been painful otherwise. Coming back to dopaminergic, you should remember, cognitive processes. Without having studied the activities of Hans Specht's prefrontal cortex, I'm almost sure that he enjoyed such Bewährungssituationen, enhancing one's self-confidence by meeting a challenge to your ever-enhancing skills. This refers to Max Weber's theory of charismatic leadership, which proves itself in crisis. Understanding dopaminergic, it is not difficult to decipher Hans Specht's love of listening and practicing music, skiing, understanding and using cutting-edge technologies. And last but not least, doing experimental physics. Apropos limitless curiosity. His love of music made him study activities of the prefrontal cortex of music lovers. So do I really have to explain what I mean by project and promise? The germs of curiosity and fluid intelligence are probably in one's genes. But nature, being generous, offers many venues of learning skills and accessing limits. So the project can only be to make best use of this, offering exciting aspects, challenging curiosity and intelligence, and not unnecessarily confining or limiting spaces, generating blind spots. Help them to find real pleasure in learning and meeting challenges. Remember, dopaminergic. The promise is that this happens again and again, and most of you have witnessed the miraculous emergence of young talents making best use of their earthbound intelligence and skills to replace us, sometimes standing on our shoulders when we are gone.
In the beginning, I told you that Hans Specht was not only a scientist, he was also a pianist. And here we see him play his Steinway B grand piano. And he did not only love music, as a scientist, he analyzed music. He did a lot of studies on musical perception and the link to neuroscience. There was a series of lectures given by Hans Specht and Hans-Günter Dosch. Both of them were working along the same line, and they gave talks in front of large audiences where they showed the effects of musical perception. And it was really interesting to listen to these particular performances. These performances took place in many places, namely, they were, oops, I'm sorry, that's going too far. For instance, here, this photo is taken from the famous Einstein lecture in Berlin, where Specht and Dosch discussed musical perception, physics, neurophysiology, and psychology. They were also invited to the Beethoven Festival in Bonn, the Loeb Lecture in Harvard, Music Festival in Verbier, Academy Traunkirchen, but they also gave talks, of course, here at GSI, at DESY, at CERN, at Munich, in Wien, and even at Gießen. I had invited both of them to give their talk on the occasion of the 400th anniversary of our university. And I can tell you, this was a physics colloquium I will never forget. We had to go to the main lecture hall with 500 seats. That was so crowded, I have never seen that before. And it was again an experience to listen to these experts studying the effects of musical perception and neurology. And this was not only in these big lectures in front of large audiences, they did very serious work, in particular together with Peter Schneider, who can unfortunately not be here today. But they published a lot of papers, very important papers in neuroscience. And I have to tell you, Hans Specht's, most cited paper is exactly this one in Nature Neuroscience, with more than 1,000 citations. Well, you heard from Axel about 674 citations, but this is even more. So he had a lot of influence, not only in physics, but also in other fields, and that shows his exceptional position as a scientist. Yeah, now after having heard all these exciting results, we should not end this colloquium in sadness, but we will again ask Utku Hasan to play the waltz in C-sharp minor from Chopin. And as I heard, Martin Specht played this piece at the last day of Hans Specht's life for him. But now we will hear Utku Hasan. Okay, go ahead.